Hey guys! In this video, I'll be going over how to code a bisection method problem in Matlab. I'm going to be using the same example that I used for my other bisection method video, which I have a link to that video down in the caption. So I highly encourage you to go check out that video because it will explain a lot more of the theory behind the bisection method. Whereas in this video, I'm just focusing on coding that bisection method example in Matlab. Alright, so let's go ahead and get started. The first thing we want to do is create a new script. And then I'm going to name it and save it. Alright, so in the lower right-hand corner of the screen, you can see the original problem statement and my basic bisection method steps that I talked about in my other video. And so the idea behind coding this problem in Matlab is that we're basically going to use the same approach. It's just that instead of writing these steps out on paper to solve the problem, we're going to let Matlab do all of the math and all the work for us. So the first thing I'm going to do for step 1 is define my givens. So I'm going to define my function as an anonymous function. So I have 2 times x raised to the third plus 5 times x raised to the second minus 6. And then I have my given lower bound, which is 0.5, and my given upper bound, which is 1.5. And then I'm told that my error tolerance needs to be less than 10%, which is the same thing as saying 0.1. Alright, so step 2 is going to be to graph my function. And this is something that my professor encouraged us to do so that we can get a visual representation of what we're doing. So I'm going to assign this graph to figure 1, and I'm going to use the fplot command because I have an anonymous function. So I'm going to feed in my anonymous function and then define my bounds on which to graph. And then I'm going to say that I want my graph to be a solid blue line. Alright, cool. Now I'm also going to do grid on so that I have grid marks on my graph and it makes it easier to see the points. And then I'm also going to do hold on so that Matlab will plot points later on in my code on this same graph. Alright, so step 3, it is going to be iteration 1. Sorry, I forgot how to spell iteration there for a minute. Alright, so I'm going to make a little note real quick just for reference that the equation for the bisection method is, so we have xr, which is our root estimate, and it's my lower bound plus my upper bound divided by 2. Alright, so you can see down in the bottom right hand side of the screen that part A for our iteration is to define the bounds for this iteration. So I'm going to call them XL1 and XU1 for my upper and lower bound. For my first iteration, my lower bound is going to be my given lower bound, and the same thing with my upper bound. Now, I know it seems kind of counterintuitive to define my bounds down here when I've already defined them up here. But when I get into the second iteration, I think it'll make a lot more sense on why it's a good idea to redefine your bounds each time. Alright, step B is to calculate the root for this iteration. So I'm going to call this XR1. And basically, I'm going to use this bisection method, or this bisection function right here, and I'm going to plug in my bounds for this iteration. So I'm going to have my lower bound plus my upper bound divided by 2. Okay, my next step is going to be to calculate the function values for this iteration. So we want the function value at the lower bound and at our root estimate. So for the lower bound, we are simply going to take and pass in xl1 into our anonymous function. And for our root function, or for the function value at our root estimate, we are going to feed in the root estimate value to our anonymous function. All right, and then step D is going to be to multiply the function terms together. So I'm just going to pick a variable. I'm going to call this M1. If I can type. There we go. And I'm going to say that M1 is the function value at our lower bound times the function value at our root. And I get that this number is -4.5. Now, I'm going to make the assumption that you already understand how to use the sign on this value to determine whether our root is in the lower quadrant or the upper quadrant. If you are a little shaky on that or you're not sure what I'm talking about, I recommend that you go watch my other bisection method video because I explain in detail in that video what I'm talking about here. But again, because in this video I'm just focusing on the code, I am going to go ahead and move along, and I'm going to make a little comment for myself that says, because this value is -4.5, that means the root is in the lower quadrant. And then I'm also going to go ahead and put a note here that says that if we need to perform another iteration, we are going to set our new upper bound equal to xr1, and our lower bound is going to be equal to xl1. And again, I am making these statements based on information that is in my other bisection method video. All right, so now we want to determine if we actually even need to perform another iteration. So this is going to be step E, where we calculate the error. And I'm going to be using the % relative magnitude approximate error. So if you remember, the basic equation for the % relative magnitude approximate error is that the error equals the absolute value, because we want a magnitude, and then we're going to have a fraction, and in the numerator we are going to have the more accurate value minus the less accurate value divided by the more accurate value, and all of this times 100. So knowing that, I'm going to pick a variable for this error, and I'm going to call it e of 1. And I'm basically going to use this equation right here and substitute in the appropriate terms for this iteration. So I'm going to have my absolute value, and my more accurate term is going to be my root estimate. And since this is my first iteration, my less accurate term is going to just be 0. And then if we run the script, we can see that our error is 100%. So I can say that because 100% is greater than the 10%, which is our error tolerance, we need another iteration. And one more step before I go ahead and move on to my second iteration is I'm going to take and plot my first root estimate on my graph. So I'm going to use the plot function because I had hold on earlier in the script. And I'm going to plot my root estimate and the function value corresponding to that root estimate. And then I'm going to say that I want this point to be a magenta colored O. So now you can see here that this is the location of our first root estimate. And this is the value that we are trying to get to. All right, cool. Now we can go ahead and move on to step 4, which is iteration number 2. And because with the bisection method, you're basically repeating the steps each time, you're just using different numbers, I'm going to take and copy and paste my code and then go through and modify it as needed. All right, so this is going to be step 4, iteration 2. And this time we are working with a lower bound 2 and an upper bound 2. And you can see back here that we defined what these values need to be. So our upper bound is going to be equal to our first root estimate. And our lower bound is going to be equal to our lower bound for our first iteration. So then I'm going to take and go through, change all of these to 2. All right, and then I'm going to go ahead and comment out this part and this part, just because they will depend on these values up here. All right, so my M value this time is 10.5. So since we have a positive value, that means that our root is going to be in the upper quadrant. And therefore, if we need to perform another iteration, we are going to set our upper bound for iteration 3 equal to our upper bound of this iteration. And our lower bound is going to be equal to XR of 2. So now we can go ahead and calculate our error. So this time, our less accurate value is going to be XR1. We can see down here that our error is 33%. And so we know that because 33% is still greater than 10%, we will need another iteration. I'm going to go ahead and plot this point though, so that I can see the difference between iteration 1 and iteration 2. And let's make this point a black O. All right, so here's our first iteration. This is iteration 2, and this is the point that we're trying to find. So this point, or this iteration, actually got us further away from the point that we're looking for, but that's all right, because let's see what happens when we do iteration 3. All right, so again, I'm going to copy and paste my code just to save myself some time. This is going to become step 5, iteration 3. And I can see back up here that I need to define my lower bound as being equal to LR2 and my upper bound as being equal to XU of 2. And then all of these numbers are going to get changed to a 3 as we are on the third iteration. And then I'm going to take and comment out my error and my plot. So this time I have an M value of 1.95. So this is a positive value, which means that again, our root is still in the upper quadrant. So therefore, if we need to perform another iteration, I know that my upper bound is going to be equal to, or my upper bound for my fourth iteration will be equal to this previous upper bound. And my lower bound for my fourth iteration will be equal to my root estimate for this iteration. So I'm going to call this E3, and now my more accurate estimate is 3, and my less accurate estimate is 2. Now I have an error value of 14.3%. So we are getting more accurate, but 14.3 roughly is still greater than 10%. So we will need to perform another iteration. The last thing I'm going to do for this step is go ahead and plot this estimate. And let's make this a red O. All right, cool. So this was our estimate for iteration 2, and then this is our estimate for iteration 3. And as you can see, we are getting closer to our actual root value. So that's a good check for you to make sure that you're on the right path. All right, and then this is going to be step 6, iteration 4. All right, and so we set up here that we are going to set our upper bound equal to x upper 3 and our lower bound equal to x root 3. So now I'm going to go through and change all of these numbers. All right, cool. I'm going to take and comment out my plot and my error for now. And so my M number is now negative 0.04, we'll say. So since this is a negative number, that means that our root is in the lower quadrant. So that means that if we need to perform another iteration, our upper bound for iteration 5 is going to be equal to XR of 4, and our lower bound for iteration 5 is going to be equal to X lower of. All right, so now we can go ahead and calculate the error. So we're going to make this 4 and 3. Oops. Now our error is 6.7%. So 6.7% is less than 10%. So that means that we have found the answer. So I'm going to take and put in a little fprintf statement here, and I'm just going to say the answer is %f, for a floating point, and then \n so that we start a new line. And then I need to tell Matlab what value to feed into this floating point space. And I want to feed in my root estimate. So now if I run my script, I have this little statement that pops out that says what the answer is. And the last thing I'm going to do is plot this point and just double check that it is right on top of where I would expect the root to be. And so I'm going to make it a green colored O. And oh, there we go. So this is iteration 4, and as you can see, it's pretty much dead on where that line crosses the x-axis. So I can confirm that I found the correct answer for this problem. So that's it, guys. I hope this video helps you better understand how to code a bisection method problem in Matlab.